So the first thing I'm going to do is tell you that this learning target, I can use differential equations to create models for population growth. Doesn't exactly describe the section very well. So I'm just going to give it, if you like to just put a title and don't want to write the whole learning target down, I would title this logistic growth. That's what I would call section 9.4. I would call this logistic growth. Okay. All ready? Blake, are you ready? Okay. All right. So before we start in with logistic growth, we're just going to review for a moment regular exponential growth. So traditionally, exponential population growth has followed the differential equation model dp dt equals kp. This is because for traditional unlimited population growth, the rate of change of the population is proportional to the size of the population. So if you have a bigger population, you have a bigger rate that it's growing. If you have a smaller population, it's growing at a smaller rate. So rate of change of the population, whenever we say is proportional to, two things that are proportional means that one is a constant multiple of the other. And traditionally in math, that constant multiple is called k. So all that means is dp dt, the rate of growth of the population, is proportional to, so equals k times, equals some constant multiplier times the actual population size at any given time. So you start with this, and then from this you can actually derive a population model. What I'd like you guys to do is go ahead and separate this differential equation and solve it. Keep the k on the side with the t. Keep the k as a constant. It's not a variable, it's a constant. So keep the k on the side with the t's and take a minute and see if you can solve this differential equation. All right, so when we separate the variables, we move the p. Fuck, I didn't want that. Goodbye. Move the p, there we go. Move the p to this side, 1 over p dp equals k dt. What's the antiderivative of 1 over p? ln p. Normally be ln absolute value p, but if p represents a population, then you don't need the absolute value because populations won't be negative. Now, you can leave the absolute value if you want, but when you drop it, you're going to get a positive anyway. So you might as well just keep it positive. All right, so p ln p equals, what's the antiderivative of k dt? kt plus c. So when we solve this for p, we exponentiate both sides. So we get p equals e to the kt plus c. And that is solved. However, I personally like to think of this as e to the kt times e to the c. And e to the c, e is a constant, right? C is a constant. So e to the c is a constant. And therefore, you end up with some constant e to the kt. So this is your PERT formula, just with different letters. But this is, most of the time in math, you'll see it as c e to the kt. But anyway, so this is PERT. So a equals p e to the rt. It's all the same formula, just different letters. All right, so this is your population model if your population was allowed to just, grow forever up, right? Okay. However, most populations don't get to go, and grow forever up. Most populations end up getting kind of limited by something that we call a carrying capacity. And whenever we are limited by a carrying capacity, we follow a different model. That model that we follow is called the logistic differential equation. So the logistic differential equation looks like that. And I want that to go into your work. So dp dt equals kp times 1 minus p over m. So that's called the logistic differential equation. P is still your population. K, I'm going to write some things down. K is actually your rate of growth. P is your population, and then M is your carrying capacity. K and M are constants. What are the two variables? P and T. P and T. How do you know? Look at your differential here. dp dt. There's your output, there's your input. P and T are your variables. All right. We got this down? All right. So we're going to start by looking at a slope field of that differential equation. So if we were to, actually it's of this differential equation. So if we were to graph a slope field for this differential equation, first of all, look at that differential equation. What's the carrying capacity? 1,000. What's the growth rate? 0.08. All right. So what happens is when you have a carrying capacity, so this right here, right, that's your carrying capacity. All right, if your population starts below the carrying capacity, which is what happens most often, then it grows until it gets close to the carrying capacity and then it kind of levels off at the carrying capacity. If it starts above the carrying capacity, it gets driven down to level off at the carrying capacity. So either way, the carrying capacity kind of serves as like a horizontal asymptote for your function. As the farther you go on the t-axis, so the farther you go in time, as time approaches infinity, your graph, no matter where you start, is going to approach that carrying capacity. All right. There are a few things that you need to know from this graph. So a few concepts that you need to know. The first is the concept of what are called equilibrium solutions. So equilibrium solutions are solutions when the population is not changing. I'm going to write that over here. Equilibrium solutions occur when dp dt equals 0. When the population is growing and it isn't not increasing or decreasing, it's just static. So if you look at your differential equation, there are two different values of p that cause our dp dt to equal 0. What is one of the values of p that would cause us to have a zero growth, or zero rate of change? Yes. 0, right? So if your population is 0, it's not growing and it's not decreasing. Okay. Yeah, all right. 1,000 is the other one, right? So if the population equals the carrying capacity, you end up with a 1 minus 1 here. At the carrying capacity, you're not growing, you're not decreasing. You're just static. You just get stuck at the carrying capacity. So P equals 1,000 for this problem, or in general, the carrying capacity. Okay, those are called your equilibrium solutions. The size of the population where it's not going to change. Okay. The next thing you need to know is there are two types of questions that the College Board will often ask about logistic models like this one. One of the questions they'll ask, even though you don't know P, right? All we know is dp dt. So without knowing anything about P, they'll ask you, hey, what's the limit as t approaches infinity of your population? So what is the limit as t approaches infinity of this population? It's 1,000. It's always equal to the carrying capacity. So sometimes they'll ask you for, so I'm going to write it again because it's that important. So sometimes they'll ask you, hey, what's the limit as t approaches infinity? And without knowing anything, if it's logistic, it's going to be the carrying capacity. The other thing they might ask you is a tiny bit harder, but once you learn it, it's really easy. So the other thing they might ask you is, what is the population size when the population is growing the fastest? Okay, so when the population is growing the fastest, that means that dp dt is a max. So we're really looking for a max of dp dt, when dp dt is a max. Well, how do we know, how do we find a max? What do? We find the derivative, we set it equal to 0, we find our critical numbers, we make a sign line, whatever it is that we do, right? So what we're really looking for is when d squared p dt squared, we're looking for when we have a point of inflection on p. We're looking for a point of inflection on p. So in other words, point of inflection on P. All right. So how do we know when a point of inflection? Oh, yeah.
Couldn't we just look at the graph and think of the slope field? Couldn't we just take whatever the highest slope is, and that is?
How do you know where the highest slope occurs? You're going to do that by hand? What if it occurs in between two of these little tick marks? Right? Yeah. So you could. That's actually a good, you're thinking out of the box. I like it. And you're absolutely right. We're looking for the highest slope, right? So we're looking for the steepest slope, but the problem is you really do need an analytical way to do it, not just plugging numbers in and sitting there comparing all the numbers, right? So just like if you were finding a max, you wouldn't just sit there and plug all the numbers in and then take the biggest one. You need a way to find it, right? So the nice thing about this is that I can show you this analytically. It's actually not hard to prove, but I'm just going to tell you the answer. So the point of inflection, and I'm going to look at this bottom graph because it's the most easy to see logistic. This guy has it also, but it kind of it's kind of a weird graph. So the point of inflection, this is where it's kind of concave up, and this is where it's kind of concave down, right? Point of inflection always occurs, and so for this guy, it's actually around here. It always occurs at half the carrying capacity. So no matter what, this is always at, half the carrying capacity. So your maximum growth rate occurs when the population is at half of the carrying capacity. So for this problem, for this example, It's when your population would be 500. Notice that doesn't give you the time, right? But it doesn't matter what curve you're on, what solution you're on. You could be at any solution on here, no matter what. Pretend that this is at 500. I just didn't draw well. But anyway, you're going to be at half the carrying capacity for that point of inflection. The time when it happens varies curve to curve, so you have to solve for time. But the actual population, the output value, is always half the carrying capacity. Yes, Keith?
So that's like a thing that's always going to be the case.
Yes.
Are they going to expect you to like explain
Nope.
more? Or
I'm just going to ask you. Yeah, isn't that nice? Yeah.
Put that in.
It's a lot of memorizing in today's lesson. Yes. Okay. All right. Okay. So 3 things we've learned. 1, equilibrium solutions occur when the population is 0 or the carrying capacity. Limit as time approaches infinity is always the carrying capacity. Maximum rate of growth or the point of inflection on your curve will always occur at half the carrying capacity. All right. Does everyone have those 3 things down on their paper? Because that's what we're about to do a million times. All right. So we've got this differential equation, but we need a solution, right? So here's the problem with the solution to this differential equation. Or is it okay if I move on? Have you all written what you need to write? Okay. I'm just giving it to you. The reason I'm just giving it to you, so if this is true, then this is true. That is the solution to this differential equation. Why do I give it to you? Because this differential equation requires partial fraction decomposition in order to solve, which you haven't learned yet. You'll learn it in BC. It'll be in your first unit next semester, right? So partial fraction decomposition, which is actually really fun. Like partial fractions, once you get to it, you're like, oh, this isn't bad, right? Keegan, have you already done partial fractions?
Yeah.
Okay, good. Yep. All right. But you haven't learned it yet, so because of that, we just give you this. Since you are unable to solve this differential equation with the knowledge that is currently in your head, you have no choice but to memorize this. Okay? It's not that bad. What does M represent? The carrying capacity. So your population is the carrying capacity over 1 plus AE to the negative KT. So M over 1 plus AE to the negative KT. This is true for any logistic differential equation. You're always going to want to write your differential equations, if they're not given to you in this format, you're going to want to write them in this format. I will tell you that about 80% of the time on the AP exam, when you are given a logistic differential equation, the College Board actually puts the word logistic in the problem. So they'll say, the following logistic differential equation is blah, 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 right? About 20% of the time, they don't. And then you are expected to, you're sitting there taking a test, right? You've got this differential equation, and it'll say, what's the solution? And you will have to recognize, oh, this is logistic. That's the solution. So it's not that often, but once in a while, you have to actually recognize that it's logistic. Now, on your test, which is when? Wednesday, we tell you every time it's logistic. So on your test, we just say logistic, logistic, logistic. And actually, there's one problem where it's not logistic, and years ago, half our students got it wrong because they kept trying to force logistic out of it. And so on that one, I even in bold letters put not logistic. so that you don't start trying to do logistic growth on it because it's not logistic. Okay. So anyway, all right. So dp dt equals kp times 1 minus p over m. M is your carrying capacity. K is your growth rate. If that is true, then p equals m over 1 plus a e to the negative kt. For all of these, what's the limit as t approaches infinity of p of t? It's m, the carrying capacity. All right. Everyone have these down correctly. Make sure you wrote them right. Okay. All right, good. So we're going to do a whole bunch of examples. By the end of the day, I bet you'll have memorized the both models. All right, so first we're going to go ahead and do the model that was graphed on that the original graph that we were showing, the slope field graph. So write the solution of dp dt equals 0.08p times 1 minus p over 1,000 if p of 0 equals 100. Then use the solution to find the population at 40 and 80 and answer the question, when will the population reach 900? So this is your logistic differential equation. What I want you to do is look at this, find K, find M, and then write an equation for P, plugging in the K and the M. You can talk to each other. Yeah, take about a minute and see if you can figure this out. Right. For this problem, what's K? 0.08. What's M? 1,000. So what number goes on top? 1,000. What number is always over here? 1 plus AE to the negative 0.08 T. Did everyone get that for your kind of initial setup? Now, we need a point to plug in so that we can find A. What point are we given? 0, 100. So the 0, is that your time or your population? 0 is time, 100 is population. So you're going to put in a 100 for your population. What's e to the 0? 1. So it's just 100 equals 1,000 over 1 plus a. See if you can find a. It shouldn't take you more than 5 seconds. I bet you could do it without a calculator. Tyler, did you already get it? It is 9. Good job. All right. So now we have the model. This is our population model. Notice, okay, this is the growth of the like this is the rate of change of the population. This is the actual population, right? So the population 1 plus a e to the negative 0.08 t. All right. So now we've got our population model. Now take a minute and see if you can find the population at t equals 40 and t equals 80. So you just plug in a 40 for, oh, whoops, I wrote a instead of 9. I don't know why I did that. 1 plus 9. There we go. Okay, so plug in a 40 for t, plug in an 80 for t, and see what populations you get.
More people than
Did the problem say to round? If it doesn't say to round, how many decimals do you have to give? 3. Did it ever even say population was representing people? It could be tape recorders, right? You guys probably don't know what that is, but anyway. Yeah, it could be anything. We don't know. So, yes, you always give decimals unless the problem says to round, right? So, anyway, so for this one, 730, P of 40, 731.603-ish, and P of 80, 985.266-ish. Any questions on plugging the numbers in? Are we all good with our calculator? Yes? I want to see nods. Yeah? Anthony, you good? You're the only one not nodding. Okay, good. All right. The last thing we have to be able to do is kind of do it backwards. So now we want to know, when is the population going to reach 900? So now, as long as you write the equation you're solving, you can solve it using any method you want. You can solve the whole thing by hand. It's not terribly hard. Or you can just solve it on your calculator. Yes?
Did you say, instead of writing all that, could you just say P of 2? Or do you have to actually write it out?
I would write out the equation you're solving.
Okay.
With the unknown variable, I would write out the equation. That's one they're kind of picky about. It's like writing an integral before you evaluate it. You have to write it. I would write the whole equation.
Even though P of 2 represents that whole equation.
Oh my gosh. You'd probably be fine. I don't like taking risks.
I like being
Okay. Call me over if you need any help with this. Oh, the charging thing. You went in to get a charge? You know you can't use your phone on the test.
Yeah, I'll try to.
You can check out a calculator if you need one. Okay. Does anyone need help solving? All good? Okay. Let's move on to the next one. It was, I got 54.930-ish. Is that what you got? Okay. All right. In the 30s, now I have to say 1930s. We're almost coming up to the 2030s. It's so weird. Okay. All right. In the 1930s, the biologist G.F. Gauss conducted an experiment with the protozoan paramecium and used a logistic equation to model his data. The table below gives his daily count of the population of protozoa. I could not imagine, like, counting protozoa, right? I don't know. Anyway. Okay. All right. He estimated the initial relative growth rate to be 0.7944. What letter is that? That's your K. And the carrying capacity would be 64. What's that? That's your M. All right. Find a logistic model for Gauss's data using P of 0 equals 2. So they're not talking about a differential equation. They're talking about the solution. They want an actual population of paramecium at any given time t. So they're looking for a model for P of t. So see if you can find a model for P of t knowing that P of 0 equals 2. You're starting with 2 paramecium. All right, what number goes on top? 6. 64. What number always goes over here? 1 plus AE to the negative 0.7944 T. All right. Okay, so there's kind of our beginning model, but now we got to solve for A, so we're going to plug in the point that we know. So when T is 0, P is 2, so we have 2 equals 64 over 1 plus A. So I know 64 over 32 is 2, so A has to be 31. All right, so now our population model is 64 over 1 plus 31 e to the negative 0.7944 t. All right, and then they said use this to predict the population after 12 days. So when t equals 12. Have you done that yet?
Yeah.
Okay. If you haven't, go ahead and take a second, plug in a 12 for t. Again, you can have part of a protozoan. I can't find mine. I'm just going to ask you guys for the answer because I can't find mine in my calculator. I want to type it all in again. Okay. So how many paramecium are in the petri dish or whatever after 12 days? 63.8566. Okay. All right. So you could have 856 or 857, right? Paramecium. All right. So after 12 days, we're pretty close to our carrying capacity. Now, if you look at the actual live data, the live data is a little bit more sporadic, right? Like for a while, there's 76 paramecium at day 9, but then it starts dropping down again. Whoa, like what did they do to each other in these 2 days, right? So then it goes all the way down to 51, and it starts going back up again, hits 70, and then in 1 day drops back down again, right? And starts growing again. So anyway, so life does not always follow the math model exactly, but if you kept them in there over infinitely many days with, proper support or whatever, they would probably reach roughly 64. So anyway, all right, those wacky paramecium. All right, now we're moving on to elk. This is an actual AP problem, but I added a few extra parts to it. All right. So, a state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. Part A, write a logistic differential equation for the growth of elk population in terms of K and P. So for part A, you're not writing P, you're writing dP dt. So for part A, you've got to write, you won't be able to find K. Yeah, well, you can, but we're not going to yet. So for part A, you're going to write dP dt equals, and you should have numbers and the letters K and P. So see if you can figure out what your dP dt would equal. I'm going to look up what time you guys are allowed to equal. If you are retaking the Chapter 6 test, I'm going to dismiss you at 10:18 because I let first period leave 10 minutes early to take the retake. But I will tell you, you don't need that extra time. First period, people actually came back with time to spare. So
during 4. So you won't need 40 minutes. You'll probably only need 20 minutes, but that's okay. I don't want to give you less, so I'm still going to let you leave 10 minutes early. Okay. So dp dt equals, so we don't know k. So we have a k and a p. And then what number always goes here? 1. It's that same 1, except in a differential equation we have a minus sign, right? And then p over 4,000. How'd you do on your differential equation?
Did great.
Did great.
Absolutely amazing.
Absolutely amazing. Good. All right, so now for part B, now you're going to write a model for the actual population only in terms of T, which means you're going to have to solve for K and A. So I'm going to kind of start you off on this a little bit. What number goes on top?
4,000.
4,000. What number always goes here? What's the sign? Plus A e to the negative k t. All right. We've got a good start. Now we need to solve for a and k. We need some points. Is there a nice point that we could start with to plug in? 0.40. Oh, wow. Okay. Yes. All right. Let's plug in the point 0.40. So when time is 0, the population is 40. So e to the 0 is just 1. I think. No, it's not 39. No. 4,000 divided by 100 would be 40, right? So A equals 99, right? And again, you can use your calculator. It's not like you have to do it. Okay. All right, so we've got our A. All right, so we're getting there. Now we need to find K. We're going to need a second point. 5,104. So after 5 years, we have 104 elk. So now we're going to say, all right, 104 equals 4,000 over 1 plus 99e to the negative 5k. We knew t, not k. Now you have to solve this for k. So take a moment, solve for k. Arrows here. How'd you do with your K? Pretty okay. Good. Okay. So now I'm going to rewrite P of T again. So 4,000 over 1 plus 99e to the negative. I'm going to round my K when I write it, but if I were to use it in my calculator, I'd use the whole big decimal, right? Okay. Yes, Ryan.
If you graph it and find it that way, it only gives you 8 decimal points, and you have
That's okay. You'll be 8 decimals is going to be okay. Yeah. All right. Okay, so we've done part A and part B. Part C, I'm going to walk you through this. Sketch a graph of the population model This is as deep as you need to go for part C. Whenever I have to sketch a logistic model, here's what I do. I'm going to erase stuff, so don't, if you're copying, just know you're going to need an eraser. Okay. So there's the general shape of a traditional logistic model, right? I graph the shape first, then I fill in my numbers to accommodate my shape. So up here, what's the carrying capacity? 4,000. So I label this with a 4,000. Pretend that that's kind of lined up nicely. All right. We didn't have any elk for negative time. So really what we need to do is just kind of erase this part of the graph and instead put our initial value for our elk population. What was the initial value? 40. That's really all you need. Like we could label the point of inflection if we want to. Let's go ahead and label it. Where's the maximum rate of elk population change? When there are 2,000 elk, they are repopulating the most rapidly. All right. No, I would not put any times in. All right. You're not going to be asked to graph on your quiz or your test or the AP exam. Like they've never ever asked for it. Maybe once. There might have been one time. I think I remember from years ago, like we're talking the 70s, I remember a grid with dotted lines. No. But of course I wasn't, is right. No, but I've taken those exams. Right?
Oh, you took them a few years ago.
I've taken them all. Yeah. All right. Okay. Part D. Find the limit of P as T approaches infinity. Write this down. You could do this. It'll take you as long as it takes to write it. What's the limit?
4,000.
4,000. It's the carrying capacity. All right. Part E. What is the population of elk when the rate of population growth is the greatest? I'm going to write it out. Max rate of growth occurs when P equals 2,000, when there are 2,000 elk. Always half the carrying capacity. The last part, at what time is the population growth the greatest? Now you have to actually do some math. So now you're going to have to set your population equal to 2,000 and solve for T. I can. Sure. Is that good? 2,000. All right. I got 3.6421 years. So it would take about 23 and a half years for the elk population to hit 2,000. How are we doing? They're not bad, right? Okay. All right. Now, one more problem, and then I'm going to release people who are going to go retake. So, when you're handed a logistic differential equation, it doesn't always look the way you want it to look. So, not always presented in the way that you're used to. Sometimes you have to do a little bit of manipulation before you get it into the right format. So, given this differential equation where y of 0 equals 25, what is the limit as t approaches infinity? Hint, it is not 50. Take a minute in your groups and see if you can figure out what you need to do to clean this up a little bit before you can answer the question. All right, what is the one thing that you know is similar to all logistic differential equations? That 1 right here, right? So we need to turn the 6 into a 1. You're not going to do it by subtracting. So what are you going to have to do? You're going to have to factor that 6 out, right? So you have dy dt equals 6y times 1 minus, and this is where students sometimes get confused. Do I divide the 50 by 6? Do I multiply the 50 by 6? If you're not sure, go ahead and do one of them. I'll tell you, you have to multiply it. So it's because you're dividing the whole thing by 6, which means you're multiplying the denominator by 6. So if you're not sure, once you've kind of done your factoring, just take 3 seconds and mentally distribute the 6 back in and see if you get what you need to get, right? So always just take a second and, okay, if I were to distribute the 6 back, would I get 6 minus y over 50 inside? Yeah, I would, so I'm good, right? Okay, do I have to find the actual population model? No? Oh, really? What's the limit? It's 300, it's the carrying capacity. All right, any questions on that? Okay, we're going to do one more example, but those of you who are retaking Chapter 6, go ahead and gather your belongings and head down to the test center. Unless you want to stay for the last. Is nobody carrying? Oh, okay. All right, let's move on. You could stay for the last. If you're retaking, honestly, you could stay for the last example and still go down and retake and have plenty of time. So, okay. Oh, wait, there's 2 more examples. I lied. Okay. So the first one is just more practice with factoring. So go ahead. You've got a logistic differential equation. They want a logistic model, which means when they're asking for, if they wanted the actual differential equation, they'd say it. They don't want it. They want the y equals. A logistic model means solve for y. So go ahead and see if you can rearrange this so that you can find your k and your m and then write a function for y. Okay, so first we have, to rewrite this. What are you going to have to factor out? 3y over 20, or 3/20ths y. Yeah. Times 1 minus y over. All right, so you're dividing each term by 3/20ths, which is the same as multiplying the denominator by 3/20ths. So when you multiply the denominator by 3/20ths, you get 240. Okay, so now we know our k and we know our m, and we can write y equals 240 over 1 plus a e to the negative 3/20 t, and then you just plug in your point. 15 equals 240 over 1 plus a. I think if I remember right, a was 15. Is a 15?
Yeah.
A is 15. So your final answer would be 240 over 1 plus 15 e to the negative 3/20 t. Oops. That's okay.
That's tough.
Small mistake.
Sorry.
Any questions? Are you kind of starting to get comfortable with the two models? Okay. All right. Good. Last one. We're not going to do this on whiteboards. We don't have time. So this is actually an AP problem from 1991. It's quick, it's fun, it's logistic. So we're going to do it. All right? Okay. So 1991 BC number 6, no calculators. A certain rumor spreads through a community at a rate of dy dt equals 2y times 1 minus y, where y is the proportion of the population that has heard the rumor at time t. What is the carrying capacity? 1. Does that make sense?
Yeah.
Yes, because 1 is the same as 100%, right? So the highest proportion of the population that can hear the rumor is the whole population, right? Okay, so there's your carrying capacity of 1. Part A, what proportion of the community has heard the rumor when it is spreading the fastest? Yeah, that's it. You just had to write the answer. Like that was all, that you didn't have to explain anything. Back in 91, the word explain like never appeared on a problem. So, yeah. All right, so what proportion? It's always half the carrying capacity, so you can either write 0.5 or you can write 50% either way. Okay, part B. If at time 0, 10% of the people have heard the rumor, find y as a function of t. So go ahead and take a minute, write your equation for y. What's your carrying capacity? 1. What number always goes here? 1 plus a e, what's k? 2, negative 2t. All right, so we have the point when time is 0. What's your actual y? 0.1, right? So you have 0.1 equals 1 over 1 plus a. So we want a to be 9, so this is 1/10, right? So a equals 9. So you get y equals 1 over 1 plus 9e to the negative 2t. All right, last part. At what time is the rumor spreading the fastest? So what are you going to set your y equal to? 0.5 and then solve for t. And then you are done with that whole AP problem. Yeah, this was no calculator.
Oh.
Yeah. So in this case, you just have to actually distribute. So you have, I would go like this. 1 divided by 0.5 is 2, so I'd have 1 plus 9e to the negative 2t equals 2. 9e to the negative 2t equals 1. Coming over here. E to the negative 2t equals 1/9. What do I have to do to both sides? ln 1/9. nt is now negative 1/2 ln of 1/9. I have a question. Is this time value negative or positive?
Positive.
It's positive, but there's a negative in front. ln 1/9 is negative because 1/9 is less than. Right. Okay. Good. That's it for the lesson. Here endeth the lesson. You are now done with all